Hello, Professor Uden and fellow teacher assistants. Today we are going to present our ENSF 612 final project. We are basing our project on the research categorizing the content of a GitHub README files. Our team consists of Bhavya Gupta, Coyote Aw, as well as myself, Michael Lee. So README.mds are one of the most important documentation for open source repositories, where it is the first point of communication between the owner of the code to its users. Now, doing the readme.md file poorly would mean that it would be very difficult for the community to learn about the open source code and use it. However, many people, myself included, are often lost to the huge sea of open source code and often don't know where to start. Not only that, there haven't been a well-defined standard that developers follow to create the README files, which makes it very hard for people to easily gauge what these repositories are exactly for. And that is why the research categorizing the content of a GitHub README files existed. And this research is used to solve and improve the readability of these README files by using machine learning to effectively predict and label well-defined and standardized categories within the README files based on its context. As mentioned from the research paper itself, the participants or the users who tested the labeling functionality based on machine learning classifications have reported increased effectiveness in information discovery. We believe that the machine learning done with this research can help evolve the GitHub ecosystem to be more user-friendly and more accessible by improving easier information discovery on the vast treasures of source code that can be found within the world of GitHub. And this is what really propels us into wanting to delve deeper into this research. So our project is basically going to be based on the research paper categorizing the content of GitHub README files. And in here, we will explore the following. First of all, we will look at how is the data being collected. Then we will compare how does our new manually annotated data compare from the original data set that they have. And then we're going to look at how is the data being pre-processed into the model, as well as looking at how does the model being performed. We will also look at how does the hyperparameter affect the model's performance, as well as explore the misclassifications that the model has when they are predicting the results of the data set. So now let us start with how was the data being collected.
In this part of the slide, I will be discussing how we're able to collect a new set of data. We use GitHub API and develop README downloader to download new set of README files from the GitHub. And we ensure that the downloaded files were randomly chosen and they are also unique. Files downloaded belong only to the software development repository and have a size that is greater than 2 kilobytes. After we have been able to download the new set of data from GitHub site, we carried out manual annotation on 189 sections of the new data, and we use Cohen kappa analysis to perform agreement analysis on the manual labeling. We were able to return an agreement of 94%. We are also able to develop a cross tabulation that shows different counts versus the expected count using IBM SPSS software. We're able to handle the disagreement between the results by revisiting those sections. and all of us were able to agree on a particular code for row section where we disagreed by using majority votes. In this part of the slide, I'll be comparing the new data set with the original data set. The original data set comprises of 393 README files, which has over 4,200 sections. The new files, on the other hand, has over 1,000 README file sections, and there is a common trend between these two sets of data. For example, the category that we categorized as how, that is code 3, account for 50% of the total count in each of these files. And we also notice that there is a similar distribution of sections across two sets of data. We will show you in the next couple of slides some charts that actually depicts how these sections were distributed in both files. This part of the presentation is showing a bar chart that represents the distribution of each section in both sets of the data. That is comparing both the original and the new data in terms of distribution of the file sections. For example, it's obvious that section 3, which is how, accounts for most of the file section in both the new and the old data set. For the old data set, we have 2467 count for the category 3, while we have 540 in the new data set. And obviously, category 8 will represent order as the least amount of counts in both the new data set and the old data set. As it was mentioned earlier, section 3 of the README file section account for over 50% in both the original data and the new data. As you can see from the pie charts, section number 3 accounts for over half of the total count, while section number 8 is the least.
During presentation 2, we dive deep into explaining the pre-processing of data and feature extraction. We had also showed working examples for each. In this presentation, we will summarize them. First, let's talk about pre-processing of data. In our feature matrix, we do two kinds of pre-processing: content abstraction and tokenization and stop word removal. In content abstraction, we replace some of the content like code snippets, numbers, images, and hyperlinks with their type. In tokenization and stop word removal, we tokenize the heading and body of README sections and remove stop words from them. In our target vector, we use multi-label binarizer to encode README sections 1 to 8, including the exclusion, into a matrix of zeros and ones. Next, let's talk about the feature extraction. We extract two kinds of features from our data: statistical features and heuristic features. Statistical features is basically the TF-IDF matrix from the abstracted, tokenized, and stop word remove content of the README section. Heuristic features are 55 binary features derived from the headings and body content separately. These 55 binary features can be categorized into 4 types, namely linguistic patterns, repository name, single word non-English heading, and non-ASCII content text.
Before looking at how our model performs, I wanted to introduce you on how we prepare the model from the original research paper and modify it to work in Databricks. Now, the author of the GitHub README content classifier has provided the source code for the classifier program on the GitHub, and as part of the requirements of the ENSF 612 project, one of the first tasks is to convert the author's program to be able to operate on Databricks. Now, there are two hurdles that we need to overcome in order for us to successfully run their code on Databricks. And they are, the first one being the current program utilizes a SQL database to store and process information, and a second hurdle being Databricks runs on notebooks that makes referencing Python module files from their file store difficult. And that is a big problem because that the original author's program consists of a lot of different modules and scripts, as well as running off on a SQL database. So to port that into Databricks poses a certain amount of difficulty. So after investigating as to how the program works, we have determined to modify one of their scripts called experiment classifier validation to meet our needs. We first copy all of the code from this file into a new file in which we name it as project_execution.py to make the changes. And to address the first point, we first use this Python file and dump their SQL query data that is needed within their classifier validation into a CSV file. And then we uploaded this CSV file to the file store within Databricks. As to addressing the second hurdle, we need to look at what files did the experiment classifier validation script that they have uses so that we can consolidate the code into one file. Now, upon looking at the file, we observe that there are two files from which experiment classifier validation gets reference from, and they are the heuristic2 and the balancer files. And both of those is basically for tweaking the feature matrix and the Y vector in order for it to make the model work. Now, after that, we then look at the code from those files and copy and reorganize the code so that everything can be running from a single file. Or in a sense, we put and consolidate all of this code into a single class. And the resulting code is what you will see in the Databricks notebooks that are linked in the final report. Now, following the general preparations that I've discussed in my previous slide, let us now talk about how do the models perform on the original data versus the new data plus the original data. Now, with the original data, we have performed model analysis of the weighted average of precision, recall, and F1 score for the models that you see in the leftmost column of the table showing in front of you right now. Now, the first four models, namely the random forest classifier, the linear SVC, the Gaussian NB, and the logistic regression, were used in the original paper. Now, the last five models, the bagging classifier, the extra trees classifier, the decision tree classifier, the ADA boost classifier, and the histogram gradient boosting classifier, are models that have not been experimented by the original paper. Note that initially the original gradient boost model is used, but Databricks terminated the cluster before the model can finish running. Histogram gradient boosting classifier is also significantly longer to complete than the other models. So, for example, to give you a glimpse of how does it compare with the other models, the histogram gradient boosting classifier took 5 hours to complete compared to 2.5 hours for random forest and only 11.5 minutes for linear SVC. But nonetheless, the histogram gradient boosting classifier can successfully complete with the scores calculated as shown in front of you. Now, as can be seen from this table, extra trees classifier actually has the highest precision, whereas ADA boost classifier has the highest recall. Now recall that precision equals the true positive over the total predictive positive, and recall equals the true positive divided by the total actual positive. Extra tree classifier is the best model to use when the cost of any false positive is high, and ADA boost should be used if we want to filter out the most false negatives. Now, for overall performance, we should instead look at what we call the F1 score, which is the function of precision and recall. So it's a balance of both precision and recall. And it would give us a more general performance of the model itself, where the formula will be seen as F1 equals to 2 times precision times recall divided by the sum of precision and recall. And from the table as shown in front of you, the top 3 models that have the highest weighted average F1 score is the linear SVC with the F1 score of 0.721, the random forest classifier with the F1 score of 0.707, and histogram gradient boost with the F1 score of 0.711. Now, in continuation of what we did in presentation 2, our manual annotation gets put back into the CSV file along with the original data within that CSV file, and then uploaded to the Databricks file store and do the modeling in with the combined data in the CSV file. Now, for the new combined data, due to additional processing time required for the addition of the new data set, we only have been able to perform validation on the top 3 models with the highest F1 score. So in this case, we choose linear SVC, the random forest classifier, and the histogram gradient boost. And as can be seen, whether or not if it's the precision, recall, or the F1 score, they only drop slightly when additional data are added. So for example, with the linear SVC, the precision dropped from 0.709 to 0.7. And they do not actually affect the order of the performance ranking of these models. So with regards to the F1 score, the linear SVC is still the best performance among those 3. So now let us talk about how does the performance of the models changed based on the choices of hyperparameters. Now, attempts have been made to explore the hyperparameters for the project, and we first explore the performance of the linear SVC model based on the choice of hyperparameters. With linear SVC, we explore the regularization parameter, or the C parameter of the model, and we explored the effects on the model when the parameter C is set to the values of 0.001, 1, 100, and 10,000. However, it seems like only the default C value, which is the value of 1, can be successfully completed, as the other C values fails to converge, as you see in the screenshot of the Databricks output as shown in front of you right now. Now, we have also tried to explore grid search with other models, such as the random forest classifier, but the code terminates on the Databricks cluster before any results are produced. Now, we will continue on investigating this issue, and we will run grid search again using Spark ML once we have the code running without errors in the Spark ML platform.
In this slide, we are going to talk about misclassifications by the best model, which right now is SVC. We selected 200 random misclassifications by the best model and compared the results with our manual classification. We will talk about a couple of examples, one in which section is getting misclassified as introduction, and other in which section is getting misclassified as references. So in this Excel, you see 2 specific examples that we want to talk about. So for this particular file, particular README section, the author talks about how backups can be made in his app. So we labeled it as 3, which means how to. But our model classifies it as 1, which means project background introduction. We think that it might be because he uses the project name in this section and gives a little background on the working of the backups. Now let's talk about this example. We have file right here. So in this section, the author talks about how Slack/command middlewares work. So we labeled it as 3, which is how to. But our model classified is as 6, which means references, getting support, more information. We think this misclassification has been done because of the words like check it out and guide, and maybe because of the presence of code snippets. Now, let's talk about some key findings. First, we find that sections often get labeled as 1, which means introduction or project background, whenever some explanation is given for some feature, process, etc. In the previous slide, we have showed you one such example. In total, we have around 54 such instances. Second, presence of links in the section could potentially bias towards section getting classified as 6, which means references, more information, related projects, getting support, etc. We have at least 14 such examples. And third, section 3, which means getting started, how to run, configuration, setup, could get labeled as section 6, which includes references and API documentation, as their differences can sometimes be narrow depending upon the README file. We have around 22 such examples. Please note that these key findings are based only on 200 misclassifications. Depending upon more data on the misclassifications, these key findings may or may not change or evolve.
Now, one useful scenario that may be useful for real-life application of this model is that it can be used to gauge the effectiveness of the README files. For example, in the world of internet marketing, we gauge the effectiveness of copywriting by its ability to sell their products, or what they call the conversion rates. Similarly, we can adopt this method by linking our model with statistics such as the number of stars in the repository or visitor stats to see what kind of information, if included in their READMEs, will increase people to visit, branch, or star the repositories. Therefore, giving information to developers as to what information they should include in their README files to maximize the effectiveness and increase popularity of their repository. To summarize, our current Databricks model have indicate that linear SVC that is initially chosen by the original author is already the most optimized model for the work that is needed. And this concludes our presentation. Thank you for listening.